Usually when we look at a piece of modern technology, like a flagship smartphone or a high-end smartwatch or even just the exposed engine of a sports car, there's this undeniable expectation of precision.
Right. Yeah, you expect it to look complicated.
Exactly. You know exactly what you're looking at. You see the brushed titanium, the chemically hardened glass, the meticulously routed wires. The engineering is completely explicit.
It's performative engineering.
Yeah. It's right there in your face.
Yeah.
Practically demanding that you appreciate, how much money and genius went into making it.
We are culturally conditioned to recognize that specific kind of complexity. I mean, we see metal and silicon, and we automatically assign value and respect to it.
But then you step away from the tech store and into the everyday world. You walk down the fluorescent lit aisle of a standard grocery store, or you grab takeout from your favorite fast food drive-thru, or you rip open a cardboard package that just landed on your porch. And suddenly, that explicit performative engineering just completely vanishes.
It's entirely hidden in plain sight.
It really is. We are looking at a vast global landscape of folded cardboard, creased paper, molded plastic that feels, honestly, it feels mundane. It feels almost disposable. Simple,
It is the absolute definition of taking something for granted. We see a brown shipping box, and our brain just registers, oh, it's a box. We don't see the math. We don't see the physics.
Exactly. But behind that quote-unquote simple box is this shadowy world of obsessive structural engineering, rigorous material science, and honestly, incredibly manipulative consumer psychology. So, welcome to another immersive deep dive. I am thrilled you are here with us today.
It's going to be a fun one.
If you are the kind of learner who wants to look past the surface of the everyday world, if you're insanely curious about how the hidden physical gears of our global supply chain actually turn, you are in exactly the right place. We're going to completely change the way you see the physical objects around you.
That is the ultimate goal. I mean, we are stepping into a liminal space where graphic design crashes headfirst into structural engineering.
Oh, I love that description.
It really is. This is a world where altering the angle of a cardboard crease by a fraction of a millimeter can save a multinational corporation tens of millions of dollars.
Wow.
And where a tiny, almost invisible fold of paper can subconsciously alter your entire perception of a product's value.
That is wild. So today's deep dive is an exploration into this hidden, highly engineered world of packaging. And our roadmap for this journey is Chapter 10 of an absolute industry Bible. It's the Graphic Design Reference and Specification Book.
An incredible resource.
Truly. Now, before we really get into the weeds of die cuts and polymers and all that, just a quick bit of housekeeping. If you enjoy this kind of obsessively detailed content and you want to actually see the incredible visual diagrams and structural blueprints we're going to be unpacking today, you should definitely subscribe to the channel.
Yeah, the visuals are amazing.
Furthermore, if you want a physical copy of this definitive design guide to keep on your own desk, and honestly, after this discussion, I guarantee you'll want to reference these geometries, you can either scan the QR code right here on your screen, or just click the book link provided below in the description.
The visual diagrams of these folding structures are genuinely fascinating. They look like architectural blueprints, but we will do our absolute best to build these three-dimensional shapes vividly in your mind's eye today.
Okay, let's unpack this. Pun very much intended.
Nice.
We interact with boxes, bags, and cartons every single day of our lives. You, listening right now, probably opened at least 3 different highly specialized types of packaging before you even left your house this morning.
Oh, easily.
Right. You poured milk from a carton, you opened the box of cereal, maybe you unwrapped a bar of soap.
Yeah.
Yet we rarely, if ever, notice the complex geometry and the highly specific, almost secret industry terminology that dictates their design.
It functions entirely as a secret language. And what is so compelling about the industry specifications we're exploring today is that they strip away the branding.
Yeah, that's a good point.
They completely ignore the colorful logos, the mascot characters, the marketing copy, forcing us to look purely at the naked architecture of the packaging.
So by the end of this deep dive, you will never look at a cereal box, a fast food fry container, or a luxury watch box the same way again. You are going to see the intentionality behind every single crease.
Absolutely.
So let's start right at the foundation. In the packaging industry, the most basic foundational type of folding carton is known as the tray. Now, when I say tray, your mind probably instantly goes to a plastic cafeteria tray. But in structural design terminology, it has a very strict definition, doesn't it?
It does. A tray is essentially a relatively shallow parton where the bottom is hinged to wide side and end walls.
Okay.
The sides and ends are then connected by a flap, a hook, a locking tab, or a lock that can either be glued or assembled entirely without glue.
Got it.
Yeah.
So if you want to visualize it, think of the tray as a stage for the product. It's shallow because its primary function isn't like deep bulk storage.
Right. Its function is presentation and immediate accessibility.
So where's some classic examples?
Oh, they are everywhere. The box your bakery donuts come in, a cigarette carton, various food service items, and the undisputed king of the category, your classic pizza carryout container.
Oh, of course.
Yeah, those are all highly specialized variations of the fundamental tray carton.
But here's where the engineering gets really clever, and this is what blew my mind when I was first looking at the schematics. We have to talk about what the industry considers no-glue marvels. Because as a designer, you are sometimes faced with a fascinating rigid constraint. Like, what happens when gluing just isn't an option?
It is a critical multi-million-dollar question because in high-speed manufacturing, introducing glue adds an entire secondary layer of logistical nightmares.
How so? Like, glue seems so simple.
Well, it adds a consumable material you have to constantly purchase. For one, it requires specific drying times, which slows down the assembly line.
Ah, right. Time is money.
Exactly. It introduces the potential for chemical interaction or contamination with the contents, which is a massive liability in food packaging. And it can severely complicate the end-user recycling process.
That makes total sense.
So eliminating glue from a carton design is often a massive win for factory efficiency and overall cost.
So, if you can't use glue, how do you keep a flat piece of paper folded into a rigid 3D box? Because one of the primary solutions mentioned is the web corner tray. These are easy erect tray cartons that assemble strictly through folded tension.
Yes, the web corner.
I'm trying to picture the geometry here. If I have a flat rectangular piece of cardboard and I fold the four edges up 90 degrees to make the walls of my tray, what happens to the extra cardboard at the four corners? It can't just magically disappear.
That is the exact spatial puzzle the structural engineer has to solve. In a standard glued box, you might just slice that corner material, create an overlapping flap, and glue it flat against the adjacent side.
Right.
But without glue, you have to utilize that excess material structurally. You take that square of excess corner paper, and the die-cut machine scores a diagonal line right through the dead center of it.
Oh, I see. So when you fold the adjacent walls up, that corner square naturally wants to fold inward on itself along that diagonal score. It's like origami.
It is exactly like origami. That little triangular fold that collapses inward is the web.
Okay, so that's the web.
Right. When you fold the main side panels up to 90 degrees, that web folds inward against the side wall. Then the top edge of the side panel, which is slightly longer, folds over the top of the web, effectively trapping it in place.
Wow.
The entire tray is structurally sound solely because of the geometric tension and the natural resistance of the cellulose fibers in the cardboard trying to flatten back out.
So the material wants to be flat, and the interlocking folds use that desire against it to maintain the rigid shape.
Precisely.
That is brilliant. It uses the material's own physical memory to lock itself. But I have to play devil's advocate here, or maybe just ask the painfully obvious question.
Go for it.
I'm looking at the specs for another glueless option called the corner lock tray. This one uses these tiny little interlocking tongue and slot joints at the corners to form the sides instead of that elegant web fold.
Yes, the corner locked tray.
And from a purely physical standpoint, it seems incredibly flimsy. It doesn't have the reinforced double wall thickness of the web corner. Why intentionally design something that is structurally weaker?
This perfectly illustrates the intense, often brutal economic calculations of packaging design. You're right, it is technically less rigid than the web corner tray. But to understand why it exists, we have to zoom out and look at the macro scale of manufacturing.
Okay, zoom me out. I want to see the big picture.
In commercial packaging, you are rarely just making one box. You are making millions, maybe tens of millions of boxes. You are buying giant, multi-ton rolls or massive pallets of flat carton board.
Right.
The two-dimensional pattern of the box, the blueprint, has to be stamped or cut out of that massive flat master sheet. If your box design utilizes big, bulky web corners, those intricate blueprints do not nest together tightly on the master sheet. You end up with large, awkward gaps of negative space between the box patterns. That negative space is scrap. It is wasted cardboard that you paid for, which now has to be recycled or thrown away.
It's like cutting circular cookies out of rolled dough. You inevitably leave all that weird diamond-shaped dough between the cookies, which is essentially wasted space until you re-roll it. But with cardboard, you can't just re-roll it on the factory floor.
That is the perfect analogy. You can't just mash it back together instantly. Now look at the corner lock tray. Because it uses these tiny, minimalist interlocking tongues and slots at the corners instead of large folded webs, the flat pattern is much closer to a perfect, unbroken rectangle.
So they fit together better.
Incredibly tightly. Those patterns nest together seamlessly on the master sheet. You are utilizing a vastly higher percentage of the raw material.
So it's a calculated sacrifice.
It is a masterclass in economic design. Over the course of a production run of 10 million cartons, that fraction of a cent saved on raw material yield per carton translates into a massive reduction in overhead.
That adds up fast.
Exactly. Yes, you sacrifice a bit of corner rigidity, but if the product inside is relatively lightweight, say a single artisan pastry or a lightweight garment, that trade-off is absolutely worth it. The packaging engineer isn't just designing a box, they are designing the invisible efficiency of the factory floor.
That completely reframes it for me. It's not just about the final shape, it's about the ghost of the cardboard left behind.
Nicely put.
Okay, so that covers the glueless world. But glue is obviously still a massive player in the industry. Let's talk about the glued titans of the tray world. The industry leans heavily on a workhorse known as the 6-point glued tray with integral lid.
Oh, that specific carton is the unsung invisible hero of the modern fast food industry.
When you look at the mechanics, it's obvious why. The pre-glued corners provide incredible structural strength. But the real magic is the assembly, right? It ships completely flat to the restaurant. But the moment a worker pulls outward on the side walls, the entire tray and lid instantly spring into a rigid, three-dimensional box.
Connect this to the physical environment where this box operates. You are in a loud, crowded, high-pressure commercial kitchen. You have a massive lunch rush. There are 20 cars in the drive-thru, and seconds matter.
Every second counts.
You absolutely cannot have your line workers spending 10 seconds meticulously folding origami web corners for a chicken sandwich. You need a vessel that goes from a flat, two-dimensional piece of paper to a rigid, secure container in a fraction of a second, using only one hand if possible.
You literally just grab the flat edges, give it a quick pull, and pop. The box materializes.
That satisfying pop is the result of incredibly precise 6-point gluing. The manufacturer does all the hard work miles away in a factory. Their machines fold the complex geometry, apply industrial adhesive at 6 highly strategic pivot points, and then press the whole thing completely flat again for shipping.
So the worker doesn't have to think about it.
Exactly. When the fast food worker pulls on the edges, the inherent geometry forces the walls to snap upward perfectly into place, and those 6 glue points act as permanent hinges that lock the tension. It requires zero training, it takes up virtually no storage space behind the counter because thousands of them can stack flat in a single box, and it provides a durable container with an attached lid.
It is the ultimate optimization of human motion. The cardboard is physically doing the labor, so the worker doesn't have to.
Precisely.
Beyond the fast food environment, there are a few other tray variations that serve very specific display functions. There's the open-ended tray, which is a glue-assembled tray, frequently used for baked goods when visual display is paramount.
Right, the bakery just drops the muffins in and runs a layer of shrink wrap or cellophane tightly over the top.
Yeah. Then there's the infold-outfold tray, which stores flat, self-erects easily, and is universally used as the separate base and lid for higher-end apparel in gift boxes.
Those specific variations are all about creating a structural frame. They don't hide the product, they elevate it. But there is one more tray style that is so deeply ubiquitous in our culture, we hardly even register it as engineered packaging anymore.
You're talking about the glue corner taper tray.
I am. These are pre-assembled, fully glued at the factory, and they feature a very specific, aggressive taper from the top down to the base.
Okay, I'm picturing it.
They stack flawlessly, and as industry guidelines note, they function equally well as a portable plate or dish. They are the absolute standard in the food service industry for serving French fries, onion rings, side salads, and other non-liquid products.
If I close my eyes and picture a classic medium fry container from any major burger chain, I mean, it really is an engineering marvel, isn't it? It seems so simple, but it solves so many problems simultaneously.
It is a phenomenal piece of holistic design.
Yes.
Let's break down the physical taper. It tapers down to a narrow base, which accomplishes 3 critical things.
Okay.
First, logistics. It allows the empty, fully assembled cartons to nest inside each other perfectly. A stack of 200 fry boxes takes up maybe 2 feet of vertical space, which is crucial in a cramped kitchen.
Makes sense.
Second, ergonomics. That narrow, tapered base fits perfectly into the natural grip of the human hand. It feels secure when you are holding it while driving or walking.
And third,
Thermodynamics.
thermodynamics, really.
Yes, the wide open top, combined with the taller back wall and shorter front wall, functions exactly like an open dish. It beautifully presents the golden fries visually, but more importantly, it allows the massive amount of steam and heat to escape immediately.
Oh, because if you trap the steam,
If you put hot fries in a closed box, the trapped steam turns them into a soggy, unappetizing mess in minutes. The taper tray manages heat, presentation, logistics, and ergonomics all in one glued piece of board.
that is just incredible. Okay, but here's where it gets really interesting, though. We are going to transition away from these open, relatively shallow trays. We are moving into a completely different architectural category, which is basic tube-style cartons.
If the tray is an open stage meant for display, the tube is a fortress meant for protection.
I love that analogy. In structural terms, a tube-style folding carton is defined as a rectangular sleeve formed from a single flat sheet of board that is folded over and permanently glued against its own edges. So you're left with a hollow rectangular tube.
Right.
But a tube is useless until you close the ends. It has openings at the top and bottom that have to be sealed up with flaps, tucks, or mechanical locks. Let's talk about the absolute baseline, the foundational pillar of global logistics. The industry calls it the skillet or sealed end carton.
This is your standard brown corrugated shipping box. The top and bottom flaps are folded over and permanently sealed using industrial glue or packing tape.
But the thing that really stands out to me is the bold claim made by packaging engineers. Most shipping cartons use this exact configuration because it provides the absolute most economical use of carton board. There it is again, that obsession with material efficiency.
And it is undeniably true. Think back to our cookie dough analogy.
The nesting.
If you take a standard shipping box and unglue the side seam, unfolding it completely flat, it forms a nearly perfect unbroken rectangle of cardboard. There are almost no weird, jagged cutouts. There are no elaborate tabs sticking out that would waste space.
No wasted dough.
Exactly. You are utilizing nearly 100% of the raw material drawn from the master roll. When you are a global shipping company moving millions of tons of goods across oceans, or when an e-commerce giant is dispatching millions of individual packages a day, the raw cost of the cardboard is a staggering financial factor.
It's massive.
The skillet carton is the undisputed heavyweight king of efficiency. It is the brutalist architecture of the packaging world. It doesn't need to look pretty, it doesn't need to be interactive, it just needs to be a cheap, incredibly strong structural brick.
But then, right next to this brutalist, purely efficient brick, we find something called the tuck-top crash base carton.
Yes.
First of all, crash base is an incredible name. It sounds like a maneuver in an action movie.
It is a highly aggressive name for a highly aggressive piece of engineering. The mechanics of it are genuinely fascinating.
I want to make sure I understand the geometry here because it's a bit mind-bending. This carton is used when ultra-fast assembly is the top priority. The cartons are heavily pre-glued at the factory and shipped perfectly flat. But when the packer opens it to assemble the tube, the base panels actually slide into position and lock automatically the moment the four sides form a square.
We saw a simpler version of this concept a moment ago with the fast food tray springing to life. But applying that automated spring action to the deep floor of a tubular carton is a whole different level of geometric complexity.
Right, because it's deep inside the tube.
Exactly. Imagine a tall rectangular shipping box. Normally, to build that box, a warehouse worker has to pop the tube open, physically fold down the two minor interior flaps on the bottom, fold down the two major exterior flaps, grab a tape gun, and run a strip of tape perfectly across the seam.
Which takes time.
That sequence takes time, and it fundamentally requires two hands.
But with the crash base, I'm trying to visualize it. The manufacturer has pre-cut and pre-glued this incredibly complex, interlocking web of overlapping panels right into the bottom of the tube.
Yes.
When the tube is squeezed flat, those bottom panels just lay passively against each other, folded in half.
Exactly. They hide inside the flattened walls. But the moment the warehouse worker grabs the two opposing folded edges and squeezes them together to open the tube into a square, crash. The changing geometry of the walls forces those internal bottom panels to swing downward, hook into each other's die-cut slots, and instantly form a solid, rigid, locked floor. It requires zero tape. It requires zero folding. It takes less than a half a second to assemble.
Like a magic trick.
Yeah.
But wait, earlier we established that complex folds waste cardboard and extra glue points cost money. So why would an e-commerce company use this instead of the cheap, efficient skillet box?
Because of the constant, unyielding tension in manufacturing, the trade-off between the cost of raw materials and the cost of human labor,
Okay.
the crash base is significantly more expensive to manufacture. It requires slightly more cardboard to form those interlocking base panels, and it requires a massive, complex, and highly expensive folding machine at the cardboard factory to apply those precise overlapping glue lines before shipping it flat. So the physical empty box itself costs the retailer more money to purchase.
Okay, so they lose money on the cardboard.
But they make it back tenfold on human capital. If you are a massive fulfillment center and your goal is to pack 10,000 distinct orders per hour, the labor hours you save by not having your workers manually folding and taping the bottoms of 10,000 boxes vastly outweighs the fractional extra cost of buying the crash-based carton. You aren't just buying a box, you are literally buying time. You are increasing your throughput velocity.
So we have the tubes, and we have the ingeniously engineered bottoms. But what about the top? How do we get into these fortresses? Because the industry dedicates a massive amount of research to the anatomy of the closure.
This raises an incredibly important question about user experience, doesn't it? A closure is never just a lid. In structural design, the closure is the primary interface.
Yeah.
It provides a temporary barrier, yes, but it also dictates the overall rigidity of the carton. In many cases, the specific type of closure completely transforms the purpose of the carton.
It is the handshake between the product and the consumer. Let's look at the standard options. We start with the absolute baseline, which is the standard tuck flap. This is considered appropriate for individually wrapped items like adhesive bandages or products housed in squeezable plastic tubes like toothpaste.
Right.
It's also universally used for dry food items like boxes of tea bags or sugar packets where daily reusability is the main goal.
A standard tuck flap is beautifully simple. It is just a primary flap extending from the top back panel with a little extra strip of material at the end that physically tucks down into the front of the box to hold it closed. It relies entirely on basic surface friction.
Yeah, pretty basic.
It is easy to open, easy to close, and you can repeat that action 100 times without degrading the cardboard. If you buy a box of chamomile tea, you're going to interact with that standard tuck flap every single night for a month. The closure absolutely must be durable and reusable.
Yeah, that makes sense.
But because it is held exclusively by weak friction, it offers zero inherent security. It requires a clear sticker seal or an outer plastic shrink wrap to ensure the contents remain intact prior to purchase.
Right, if you drop a box of bandages on the floor, the impact will likely cause the friction flap to just pop open and spill everything. So if a brand needs slightly more security without adding the cost of glue or stickers, they upgrade to the slit lock tuck.
The slit lock, yes.
The applications are similar to the standard tuck, but the slit lock provides a much more secure mechanical seal. Let's visualize the difference.
This is a beautiful piece of subtle, almost invisible engineering. At first glance, it looks identical to the standard tuck flap, but you have to look closely at the two smaller side flaps, the dust flaps that fold in first.
Okay.
A structural engineer has added tiny, highly precise slits cut right into their edges, and on the main top tuck flap, they have added tiny little protruding shoulders.
Okay, I see it. So when you push the main tuck flap down into the box, those little shoulders slide past the edge and physically lock into the slits on the dust flaps.
Exactly. It still relies on friction, but it is mechanical interference friction. You can actually hear and feel a subtle, satisfying little click when you close it.
Oh, I know that click.
Right. If you drop that box, it won't just pop open. It requires deliberate, angled, pulling force from a human finger to disengage the shoulders from the slits.
But what if you need even more security? What if the danger isn't the box dropping, but the product inside trying to burst out?
Oh.
That brings up the tab lock.
Oh, yes.
The addition of specific slits and a prominent locking tab provides serious protection against the lid being forced open by inside pressure from the contents.
Imagine a carton stuffed to the absolute bursting point with something dense and heavy, like a bag of specialized hardware or densely packed powder. The internal product is physically pushing outward against the lid, constantly trying to escape.
It's bulging at the seams.
A standard tuck flap would fail immediately under that pressure. A slit lock might hold for a while, but eventually the constant outward pressure will warp the cardboard and it will slip. The tab lock adds an actual physical tongue, a prominent arrow-like tab that forcefully slots into a tightly fitted corresponding hole on the front panel.
So it anchors it.
Yes. The only way that box opens from internal pressure is if the cardboard itself physically rips in half.
Speaking of ripping, that transitions us into the dark arts of packaging. Tamper evidence. I want to talk about the postal lock.
The postal lock is intense.
The industry describes this as a completely tamper-proof option that features an aggressive arrowhead tab. You push it in to lock it, but the only way to open it is to physically tear the tab, providing undeniable proof of entry. Wait a minute, though. As a consumer who cares about the environment, isn't designing a package that must be aggressively destroyed to be opened inherently wasteful? Why create single-use destructible closures?
That is a very valid pushback, and it highlights the constant battle between sustainability and consumer safety. The postal lock isn't designed to be eco-friendly, it is designed to manage human anxiety.
Human anxiety, what do you mean?
Yes. Think about the history of over-the-counter pharmaceuticals or packaged food safety. We all share a deep primal anxiety about contamination.
Oh, for sure.
When you buy a bottle of pain relievers, you need absolute, unshakable confidence that no one has opened that box and altered the medicine before you bought it. The postal lock uses a sharply angled arrowhead tab pushed through a very tight slit.
Okay.
Because of the angled geometry of the arrowhead, it slides in relatively easily during factory packing. But the flat back of the arrowhead catches against the cardboard. It is physically impossible to pull it back out smoothly. When you, the consumer, forcefully rip it open, you are actively destroying the lock. And that destruction is not a flaw, it is the primary feature. It is a one-time use, sacrificial seal of trust.
Okay, that makes total sense. The violently torn cardboard is communicating a message. It's saying, I was safe until you got here.
Exactly.
Which brings us to what I consider the absolute masterclass in closure engineering. The humble, everyday cereal box.
It is a remarkable piece of multi-stage technology, isn't it?
We take it completely for granted. We just rip it open while we're half awake in the morning. But the industry outlines 3 distinct, highly evolved closures used specifically for cereals, crackers, and detergents. Let's break them down, starting with the pull strip or zipper carton.
Oh, the zipper carton.
This provides an irreversible, highly satisfying method of opening, commonly used to prevent tampering, and is suitable for foods contained in an interior pouch.
You see this on a lot of premium crackers, cookies, or overnight express mail envelopes. It has 2 parallel lines of tiny perforations cut into the cardboard, terminating in a small pull tab at one end. You grab the tab, pull, and a precise strip of cardboard zips right off the box. It provides great haptic feedback.
It really is incredibly satisfying to open. But there is a massive structural caveat here. The engineers specify that for a pull strip to work, all other top flaps absolutely must be heavily glued or permanently locked down. Why is that?
That is pure physics. The pull strip only works if the box beneath it is perfectly rigid.
Right.
The perforations are designed to tear under localized tension. If the top flaps aren't glued down solid as a rock, pulling the strip won't tear the perforations, it will just awkwardly pull and warp the entire top of the box. The surrounding structure must provide unyielding resistance for the zipper to function cleanly.
Next in the cereal aisle is the pour spout container. This involves precise square lines cut along the container's top and side that allow the consumer to push inward, breaking the seal to form a spout, allowing them to pour the contents in a controlled manner. It's heavily used for bulk granular items like oatmeal or powdered laundry detergent.
This closure relies entirely on the microscopic precision of the die cutting machine. The blade cuts deep into the cardboard, but purposefully stops fractions of a millimeter before going all the way through.
So it weakens it, but doesn't cut it.
Exactly. It weakens the internal cellulose fibers just enough so that when you push with your thumb, the cardboard yields and snaps cleanly along a very specific predetermined geometric shape, usually a triangular spout. You aren't just opening the box, you are physically transforming the shape of the box into a specialized tool. It becomes a pitcher.
And then we arrive at the granddaddy of them all, the absolute pinnacle of breakfast engineering. The industry refers to it by a very clunky name, which is the partial overlap seal end with lock tab and lock slot.
It is quite a mouthful, but in engineering, terminology must be perfectly descriptive.
It really is. This closure is the absolute standard for items housed in a moisture-proof pouch, like cereal or graham crackers. Here is the magic. The top flaps are heavily glued shut at the factory to prevent tampering and provide rigidity prior to purchase.
Right.
But baked into those flaps is a secondary system, a lock, tab, and slot, that serves as a reusable closure after the glued carton is torn open.
What is genuinely fascinating here is how this specific cardboard design manages dual states of existence.
Yes, dual states. I love that framing. Explain the dual states to us.
Think about the journey of a box of cereal. State 1 is the grocery store. When that box is sitting on the shelf, its primary job is extreme security, structural integrity, and brand display.
It has to survive a lot.
It has to survive being palletized, shipped across the country in a truck, stacked 10 high on a shelf, and sitting there for months. It cannot fail. So the manufacturer completely glues the top flaps down. It is effectively a sealed, impenetrable brick. To get into it the first time, you have to physically break the industrial glue seal, violently tearing the cardboard flaps apart. It is highly tamper-evident.
But once you finally get it home.
Exactly. Once it crosses the threshold of your kitchen, its job changes entirely. State 2 is the pantry. You absolutely do not want a sealed, impenetrable brick in your pantry. You want easy, casual, daily access.
Right, you want to just reach in and grab it.
So, built secretly into those flaps that you just tore apart is a secondary system. A little protruding cardboard tab on the front flap and a corresponding die-cut slit on the back flap. Once the glue is broken, the box seamlessly transitions into a reusable, friction-locked container using that tab and slot.
That's so smart.
It goes from Fort Knox to a casual, open kitchen cabinet instantly. The engineering forethought to plan for the package's afterlife is astounding. And notice how the industry guidelines constantly mention the interior moisture-proof pouch.
Right, I noticed that. It specifies the interior pouch for almost all the cereal and cracker closures.
Yeah.
Why separate them? Why not just make the box moisture-proof?
Because the cardboard box is doing all the structural heavy lifting, the vertical stacking strength, the vibrant billboard branding, the tamper evidence. By offloading those physical jobs to the cardboard, it frees up the internal plastic or wax pouch to do exactly one highly specialized job, which is act as an impenetrable atmospheric barrier to keep the moisture out and the food perfectly fresh.
So they work together.
It is a specialized, symbiotic, two-part packaging ecosystem. The box protects the bag, and the bag protects the food.
Okay, let's pivot. We've spent a lot of time talking about standard, rigid geometric boxes, like the flat trays and the right-angled tubes. But what happens when you have a product that is just weirdly shaped? Or maybe it's soft, or highly fragile, or needs a very specific presentation. I want to move away from brutalist efficiency and into the realm of custom geometry. Let's talk about folders, sleeves, and die-cut wizardry.
Oh, this is where structural designers really get to flex their creative muscles and treat paperboard like a sculptural medium.
The industry has some really elegant, almost poetic solutions for soft goods and flat items. The first one that caught my eye is the pillow pack.
I love the pillow pack.
The structural description states this functions exceptionally well for packaging soft items like premium clothing, silk scarves, or small high-end pieces like artisan soaps. It is easily assembled by squeezing the ends, and crucially, it can be shipped and stored in a completely flat-packed state. I want you, the listener, to picture a high-end gift card box or a luxury hotel soap. Doesn't look like a box, it looks like a gently inflated, curved pillow. How do they achieve that with stiff cardboard?
The pillow pack is gorgeous because it defies our expectations of cardboard. It relies entirely on the physics of curved score lines. Instead of folding straight, harsh 90-degree angles, the manufacturer's die scores a perfect, sweeping arc into the cardboard at both ends.
A curved score line.
Yes. When the packer pushes the ends inward along those arcs, the curved scores forcefully push the flat center panels, bowing them outwards. It creates a convex, three-dimensional inflated shape out of a totally flat board.
It creates incredible physical tension. When you hold a pillow pack, the whole package feels springy and alive in your hands. It resists your grip slightly, and because there are no harsh, aggressive right angles, it just feels inherently more premium, more organic.
And as the logistical guideline always note, it flat packs brilliantly. The ability to ship 100,000 flat, unpopped pillow packs in a single small pallet is always the holy grail of packaging logistics.
Of course.
Another beautiful solution for flat items is the shallow folder. This makes intensely economical use of resources for packaging ultra-flat items like luxury hosiery, silk ties, or high-end documents. Its simple tuck-in closure can be sealed with a sticker or replaced with a foil drip for security.
A folder is basically just a piece of cardboard that wraps around the item like a tailored suit. It uses the absolute bare minimum amount of material necessary to protect a flat object. It's like a book cover without the pages. But let's talk about the real wizardry here, die-cut wizardry.
A die cut, for the listener's reference, is anytime a manufacturer uses a custom-shaped steel blade, a die, to punch out specific intricate holes, windows, or locking shapes from the cardboard sheet.
Right, and there are 3 examples of die-cut engineering that absolutely blew me away. First, there's the open-end sleeve with finger holes. The structural manual simply notes that strategic finger holes and open-end construction allow easy sliding access to the object housed inside the sleeve. It sounds incredibly basic, like just punch a half circle in the cardboard.
Yeah, but psychologically, it changes everything.
It does. It adds a crucial tactile element. By carving out that negative space, you are physically inviting the user's thumb to pinch and pull. It is an affordance. It turns a static box into an interactive drawer. It changes the unboxing from a clumsy chore to a smooth, premium experience.
But the next one, this is one where I had to stop and just stare at the diagram for 5 minutes. The light bulb sleeve.
Ah, yes, an absolute triumph of structural tension and minimalist design. The engineering text states, these specialized designs use inner-folded panels and strategic die cuts to protect and physically immobilize fragile light bulbs. The geometry can be modified to suit similarly fragile, oddly shaped products.
Let's truly break down the sheer, almost impossible audacity of the light bulb sleeve. You have a highly fragile, rounded, bulbous glass sphere permanently attached to a narrow metal base. You need to ship this inherently weak object in massive global quantities as cheaply as humanly possible and without it shattering.
Which sounds impossible.
If you just drop a light bulb into a standard empty square tube box, it will rattle around against the hard walls, impact the sides, and shatter instantly.
Unless you fill the box with external padding, like bubble wraps, styrofoam peanuts, or molded plastic trays. But those cost extra money, they add weight, and they are generally terrible for the environment.
Exactly. The engineer's constraint was protect this glass sphere using only the thin cardboard of the box itself. So what did they do? They took a single, flat piece of relatively thin, cheap carton board. They die-cut a very specific, intricate pattern of oval holes and slotted lines, and they added a series of complex inward-facing folds.
Okay, I'm with you.
When you wrap that single piece of board around the bulb to form the square sleeve, those internal flaps physically fold inward toward the center of the box.
I'm trying to visualize the folds that they kind of interlock around the base of the glass, right?
Yes. They fold inward and grip the narrow metal neck of the bulb incredibly tightly. At the same time, the die-cut oval holes on the side walls allow the widest, most fragile part of the glass sphere to peek out just a fraction of a millimeter, relieving direct pressure.
Wow.
The internal panels create a physical buffer, suspending the bulb directly in the dead center of the square tube.
It creates a little shock-absorbing cardboard hammock. The bulb is floating in midair inside the box.
It physically immobilizes a fragile glass object against drops and impacts without needing a single piece of external foam or plastic padding. It is the purest definition of doing more with less. It utilizes the negative space, the precise angle of the folds, and the structural tension of the paper itself to create a protective force field.
Which leads perfectly into the final piece of custom geometry I want to highlight, which is the bottle hanger. The specs describe it as a minimalist one-piece construction that lends itself to a variety of lightweight cylindrical items and provides maximum product visibility.
Think about walking down the travel aisle at a pharmacy. You see those tiny 2-ounce bottles of shampoo or lotion hanging vertically on a metal peg. They aren't enclosed in a box.
No, they're just hanging there.
They just have a meticulously folded, die-cut piece of cardboard tightly looped over their plastic neck, extending upward with a hole punched in it for the peg.
The structural minimalism is just stunning. The plastic bottle itself becomes its own packaging. The cardboard is merely an accessory. It provides a structural hook and just enough surface area to print a barcode and a tiny brand logo. It is almost invisible packaging.
And that really is the ultimate philosophical goal of good packaging design. You want to use the absolute minimum amount of planetary material required to achieve the necessary physical protection, retail display, and logistical security.
Okay, we've spent a massive amount of time talking about folding flat sheets of paperboard, bending it, scoring it, tearing it. But we are about to hit a massive philosophical shift in packaging strategy. Up until now, everything we've discussed, the trays, the tubes, the sleeves, has been folded from flat sheets by the end user or the factory packer. Now we are entering the world of rigid, three-dimensional, unyielding luxury. We are talking about the setup box.
This represents a completely different paradigm. We are moving from the economics of flat packing to the psychology of permanence.
The structural definition for basic setup construction is vastly different from a folding carton. It says a simple setup box involves taking a sheet of very thick, rigid box board, scoring it so that the sides can be folded at sharp right angles to the base.
Quite thick.
The side panels are then physically fastened at the corners with strong tape, fabric, or metal stays. Then, the entire assembled rigid box is covered with a separate pre-cut sheet of highly decorative paper that is adhered to the outside and meticulously wrapped around the box edges to hide the seams.
Think about the iconic white box your smartphone comes in, or the heavy, textured box holding an expensive piece of jewelry.
Yeah, you never throw those away.
You really don't. The most crucial logistical distinction here is explicitly noted in the industry guidelines. Unlike folding cartons, which are universally delivered flat to save space, setup boxes are delivered from the manufacturer to the brand as a fully formed, three-dimensional product, ready to be filled with merchandise.
That is a staggering logistical penalty. You are literally paying to pack, ship, and store thousands of cubic feet of empty air, from the box manufacturer in China to the product manufacturer in California. The shipping costs must be astronomical compared to flat cardboard. Why on earth would any rational company agree to pay to ship empty air?
Because they aren't paying for logistics, they are paying for human psychology. They are paying for the perception of rigidity. The guidelines specifically note that the inherent structural strength and decorative quality make them highly suitable for luxury cosmetics, gourmet candy, and high-end jewelry. The text states, setup boxes instantly add an upscale look to gifts and luxury items.
Right, it's entirely tactile. When you hold a folding carton, even a really nice expensive one, if you squeeze it slightly, there is a tiny bit of give. You can subconsciously feel the hollow tension. Your hands know that it was once a flat piece of paper.
Exactly.
But when you hold a setup box, the thick, unyielding box board, the reinforced paped corners, the seamless, tightly wrapped decorative paper, it feels architectural, it feels heavy, it feels permanent.
It confers massive weight and cultural importance to whatever is hidden inside. When you hand someone a setup box, you aren't just giving them a consumer product, you are presenting them with an artifact. The setup box acts as a permanent display case.
Let's look at how structural designers manipulate these rigid boxes to showcase the product. The specs mention the display carton, where the extended lid flap opens on a hinge to reveal a recessed display area. Because it's cut from a single sheet and wrapped, it provides an incredible unboxing reveal.
When you open the lid of a display carton, you don't throw the lid away. You fold it back, and it becomes a vertical billboard, a little theatrical stage backdrop for the product sitting nestled in the recess.
They also utilize complex geometries, like the six-sided carton with push-in closure. It uses small, rigid die-cut triangles for closing, glued heavily on the sides, and breaks entirely away from the standard square shape. It commands attention because it is a hexagon or an octagon. But my absolute favorite psychological trick in this entire section is the use of raised platforms.
Oh, this is pure, unadulterated product manipulation, and I mean that in the best way possible.
The design specs highly recommend the triangular box with a raised platform, noting the deep lid makes it suitable for showcasing a tall perfume bottle. They also highlight the lidded box with a raised platform, which works perfectly as a means of showcasing luxury watches, heavy jewelry, or other valuables. The platform surface can even be die-cut with tiny slits for firmly holding rings.
I want to ask you a psychological question. Why do humans put things on physical platforms?
To elevate them.
Yeah.
To literally raise them above the mundane. To say to the viewer, look at this specific object. This is important. This is special.
Exactly. When you open a standard flat folding carton, the product is just sitting there resting at the absolute bottom of the box, usually hidden in the shadows of the sidewalls. It feels like storage.
Yeah, just functional.
But when you ling the heavy lid off a setup box with a raised platform, the product is physically lifted up to meet your eye line. It is suspended securely in the middle of the box, catching the light.
It creates a massive buffer of empty, negative space all around the item. It is the packaging equivalent of putting a velvet rope around a Renaissance painting in a museum. The sheer amount of empty space inside the box commands respect for the small object in the center.
And practically, it offers incredible protection. A delicate mechanical watch suspended firmly on a raised platform will not bang against the rigid outer walls of the box if it gets dropped in transit. The empty space acts as a crumple zone. But the psychological effect is the primary driver. The platform turns standard retail merchandise into a coveted treasure.
The rigid box section finishes with a few other permanent forms. The hinged lid box, which is ideal for heavy items or important documents because of its sturdy, book-like nature. And the tube and slide, which functions exactly like a giant premium matchbox, perfect as a secure container for loose items. Again, the running theme is rigid, permanent, premium.
So we have thoroughly explored the intricate folding of flexible paperboard, and we've unpacked the psychology of rigid boxboard. Where does the industry go from here?
We have to pivot to the modern, high-volume mainstays of global packaging. We are moving away from paper entirely. We are entering the realm of plastics, bags, and flexible forms. This is where the sheer mind-boggling volume of modern commerce truly lives.
Paper and cardboard are incredible, but they have hard physical limits. They are terrible at holding liquids for long periods, they degrade under high moisture, and they cannot provide the extreme, airtight chemical barriers required for many modern foods and household chemicals.
The industry specifications start by categorizing common styles of stock plastic containers. Now, stock just means off the shelf. A brand or a manufacturer doesn't have to spend hundreds of thousands of dollars to design and mill a custom steel injection mold. They just open a catalog and buy millions of these standard pre-engineered shapes. The baseline shapes are simple: oblong, oval, round, and square.
But the real beauty is in the wonderfully specific, highly evocative industry names provided in the catalogs.
Oh, the poetry of industrial plastic catalogs. Listen to these specific shape names: Lexington Round, Pistol Grip Sprayer, Boston Round, Modern Carafe, Handle Wear Slant.
Pistol Grip Sprayer is aggressively literal. It tells you exactly how your hand should interface with it. But a name like Boston Round or Lexington Round, those represent deeply embedded historical industry standards.
I've always wondered about the Boston Round. It's just a bottle, right?
Yeah.
Why is it a specific standard?
It is not just a bottle, it is a highly engineered pressure vessel. Look at the specific curvature of the shoulder, the way it slopes from the neck down to the straight walls. That curve isn't just an aesthetic choice. It is designed to perfectly distribute downward pressure so the bottle doesn't crush when thousands of them are stacked on top of each other on a pallet.
Wow, never thought of that.
Historically, that specific gentle curve allowed thick glass to be blown more evenly by apothecaries in the 19th century. When the industry transitioned to plastic, they kept the exact geometric standard because it was structurally perfect. It implies medicine, tradition, and safety.
That is fascinating. It's a ghost of glassmaking surviving in modern plastic. The design manual gives a massive, glaring piece of advice for designers working with stock plastics. It says, check with specific manufacturers for more specific information on capacity range, container materials, and barrier capabilities. Why is that so critical?
Because unlike cardboard, which is essentially just mashed up wood pulp, plastic is not a single material. It is a massive, incredibly complex family of distinct chemical polymers. High-density polyethylene, polyethylene terephthalate, polypropylene, they all behave wildly differently.
So you can't just pick any plastic.
Absolutely not. Do you need to keep ultraviolet light from degrading the liquid inside? Do you need an absolute oxygen barrier to keep food from oxidizing and spoiling? Does the plastic need to chemically withstand the highly acidic, corrosive nature of an industrial cleaning chemical? A designer can pick a beautiful modern carafe shape from the catalog, but if they choose the wrong polymer resin, the chemical inside might literally melt through the bottle, or the bottle might collapse inward as the oxygen is absorbed.
It's a chemistry test, not just a design choice. Okay, let's leave rigid plastics and look at flexible forms, bags. Let's start with paper bags. I want to challenge you, the listener, right now. Picture the standard brown paper grocery bag. We use them all the time, we rip them, we recycle them. But how is a paper bag actually made? The manufacturing process is an incredible feat of continuous engineering.
It really is an incredible piece of continuous motion physics. It's mesmerizing to watch.
The engineering text breaks down the process perfectly. It says paper bags are constructed from a continuous web of paper. It doesn't start as sheets, it starts as a massive, miles-long, multi-ton roll of craft paper. This flat web of paper is pulled into a machine at blinding speeds and physically curled and formed into a continuous hollow tube. It is then glued continuously along the overlapping edge to form a permanent back seam.
So now, inside the factory, you have an endless hollow paper tube flying through the machinery at maybe 50 miles an hour.
Right. Then the text says the continuous tube is torn to a specified length, frequently against a serrated bar.
And that detail right there, the tearing, is a stroke of manufacturing brilliance.
Yes. The text explicitly points out the result, which gives the bag a sawtooth edge. I want you to think about this. If you have ever looked at the top edge of a paper grocery bag, or brown takeout bag from a restaurant. It almost always has that zigzag sawtooth cut. For my entire life, I thought that was just a stylistic, rustic choice by the brand, or maybe a safety feature to prevent paper cuts. But no, it is a direct, unavoidable byproduct of the extreme manufacturing speed.
Exactly. Think about the physics of a steel cutting blade. If you have a guillotine blade cleanly slicing through thick paper 50 times a second, the friction is immense. The blade will dull incredibly quickly, requiring the factory to shut down the entire multi-million-dollar line constantly just to sharpen the knife.
And shutting down the line costs money.
Exactly. But a serrated bar, you don't slice with it, you pull the tension paper web against the teeth and it physically rips. A serrated tearing bar almost never needs to be sharpened. The sawtooth edge on your grocery bag is an artifact of the machine's absolute necessity, not an aesthetic design choice.
Pure, unadulterated efficiency. Once the tube is torn to length, the text notes the bottom end is folded over in a complex pattern and glued to form the base. The industry categorizes paper bags into three main structural styles. Let's break them down. First, flat bags. They are incredibly inexpensive, make highly economical use of raw materials, and are exclusively for flat, lightweight items like bakery cookies, greeting cards, or small souvenirs. It is basically just a flattened paper tube glued shut at one end. No depth, no structure.
Then we step up in complexity to square or pinch bottom bags. The guidelines note these accommodate bulkier items and work exceedingly well as shopping bags for single purchases of garments or hardware. The key structural difference here is that they feature gussets.
Gussets. Explain a gusset for us.
A gusset is an inward-facing, V-shaped, folded expansion panel on the left and right sides of the bag. When the bag is empty, the gussets fold flat. But when you put a bulky item inside, those accordion-like folds expand outward, giving the bag massive internal volume and depth. However, in a pinch bottom bag, the bottom is still just pinched flat and glued. It has volume, but does not have a flat floor. It cannot stand up on its own.
Which brings us to the absolute king of paper bags, the automatic bottom or self-opening style, which the industry universally abbreviates as SOS. The text notes these are constructed with a complex, rigid bottom, often made of heavy-duty craft paper to serve as load-bearing grocery bags, or fitted with attached twisted paper handles to serve as premium retail shopping bags.
Self-opening style is a brilliant descriptor. It means that when the cashier grabs the flat bag and gives it a sharp flick of the wrist, the air rushes in and the complex pre-crease origami folds at the bottom instantly snap open and lock to form a perfectly flat rectangular structural base. The bag stands up proudly by itself on the counter, its mouth wide open, ready to be loaded rapidly with heavy cans and boxes.
The design guidelines highlight a crucial, highly specific rule for designers when dealing with bag specifications. If you are ordering custom bags, dimensions must be rigidly specified in a specific order. Face, which is the front panel, width, which is actually the depth of the side gusset, and length, which is the height. But there is a massive, expensive trap here that catches novice designers. The text explicitly warns, note that length is measured differently for a square pinch bottom bag and for a self-opening SOS bag. The length of the continuous tube before it is formed into a bag is sometimes given by the manufacturer, and this should not be confused with the finished length.
This is where understanding the physical manufacturing process saves you thousands of dollars. Because the finishing process for an SOS bag requires intricately folding a large section of the bottom tube upward and gluing it to form that flat, rigid floor, it actually eats up a significant amount of the raw tube's length.
Oh, because it folds into itself.
Right. If a junior designer orders 1 million printed bags expecting 12 full inches of usable internal height based on the tube length spec, they are going to be in a panic when the finished bags arrive and the usable space is only 9 inches deep. Their product literally won't fit.
It's those tiny, crucial physical realities of the machine that make or break a design. Finally, the guidelines briefly touch on plastic bags. It says they are manufactured from extruded plastic tubing or from a continuous flat web that is folded over and joined at a back seam. The ends are generally heat sealed to complete the closure.
Heat sealing is the plastic manufacturing equivalent of gluing, but it's far superior. They use heated metal bars to instantly melt the polymer layers directly into one another, creating an absolute, airtight, permanent waterproof bond.
The specs mention plastic bags can be flat or feature gussets just like paper, but the closures are vastly different. It lists a variety of highly specific closures like wicketed snap fasteners, board headers, and carriers. A board header is a classic retail solution. It's just folding a piece of rigid printed cardboard over the open top of the plastic bag and heavy-duty stapling it shut, often with a sombrero-shaped hole punched in the cardboard to hang securely on a retail peg. It is cheap, highly visible, and effective.
And we should definitely clarify wicketed bags, as they are a staple of industrial food packing. Wicketed bags are pre-stacked together in bundles of hundreds, held together by a thin metal wire loop, the wicket, that passes through the top lip of the bags.
Like a stack of papers on a ring.
Exactly. In a high-speed environment like a commercial bakery packing thousands of loaves of sliced bread an hour, the packer or the machine can blast air to open the top bag, slide the bread in, and seamlessly tear that single bag right off the wire wicket in one fluid fraction of a second motion.
Wow. We have covered an absolutely immense amount of structural, geometric, and psychological ground today. Let's do a quick recap of our journey through the hidden world of packaging. We started by looking at the sheer, almost impossible genius of a glueless web corner tray, a structure held together entirely by the origami tension of the paper itself. We explored the high-speed, labor-saving deployment of the tuck-top crash base carton, and we admired the brutalist 100% material efficiency of the standard shipping skillet.
We analyzed the intricate, deeply psychological dual-state security of a cereal box closure, watching it transform from a tamper-proof, glued factory vault into a casual, reusable, friction-locked pantry container.
We marveled at the die-cut wizardry that can suspend a highly fragile glass light bulb in midair using nothing but folded paper hammocks, and we unpacked the intense psychology of luxury and permanence inherent in rigid setup boxes that use raised platforms to demand respect for the product. And finally, we tracked the blistering speed of a continuous web of paper to understand exactly why your grocery bag has that iconic, sawtooth serrated edge.
If we bring this all back to you, the listener, the core takeaway here is that knowledge is truly most valuable when it is actively applied to the physical world around you. You are no longer just a passive consumer, you are now an insider.
That's right.
You have the secret vocabulary of the industry. The next time you open a package, you are not just going to see a piece of disposable cardboard. You're going to look closely and see score lines, tuck flaps, gussets, and mechanical slit locks. You are going to recognize the invisible hand of the structural engineer whose sole job was making your life easier, your unboxing experience more premium, or keeping your product perfectly safe.
You are going to appreciate the unseen, massive intelligence baked into the everyday objects we discard. I want to leave you with one final, provocative thought to mull over. We spent a lot of time talking about how a simple slit-lock tuck, or suspending a watch on a raised platform inside a heavy setup box, can entirely change human perception regarding a product's inherent value and safety. But the entire landscape of how we acquire things is shifting massively beneath our feet.
That is a very astute point. The context of the package is changing.
Exactly. As we transition globally to buying more and more of our goods online, clicking a button rather than picking a vibrant, glossy box off a physical retail store shelf, how will the physical unboxing experience have to evolve? Think about it. When the brown corrugated shipping carton, that brutalist, ugly skillet box, is the very first physical interaction you have with a luxury brand, will that shipping carton eventually be forced to become the display carton?
That's the big question.
Will brands have to engineer a way for the brown cardboard box to adopt the premium architectural psychology of the luxury setup box? How do you make a shipping brick feel like a velvet rope? It is something fascinating to keep an eye on the next time a battered package arrives on your doorstep.
It is the defining question for the next decade of structural design, bridging the gap between the brutalism of logistics and the luxury of the reveal.
Thank you so much for joining us on this incredibly deep dive into the hidden architecture of Chapter 10 of Graphic Design Reference and Specification. If you found yourself nodding along, trying to visualize folds, or having those mind-expanding aha moments about everyday objects, please remember to hit subscribe on the channel so you never miss an exploration.
Thanks for listening, everyone.
And seriously, if you want to see the actual blueprints and master this visual language yourself, grab a physical copy of the book. Just scan the QR code right here on the screen, or click the book link down in the description below. Keep questioning the hidden geometry of the world around you, and we will catch you on the next deep dive.